Hi, Assalamualaikum, Dr. Fawazi and my fellow friends. On this weekly presentation assignment, my group will be presenting Chapter 12, which is Composite Fabrication Processes and Adhesive Bonding. My name is Syairul Islam, along with Ahmas Asyraf, Danish Daniel, and Duratul Athiqah. Composite fabrication processes and adhesive bonding is two different things but related and need each other. Composite fabrication encompasses various techniques leveraging constituent materials' unique properties, while adhesive bonding is crucial for seamlessly joining different materials. Composite materials consist of a matrix and reinforcement chosen to complement each other's mechanical properties. Combining these materials result in composites with high tensile and compressive strength and resistance to bending. Lamination. Lamination is a foundational method in composite fabrication where materials are layered to attain specific properties. Plywood, recognized for its strength and stability, finds extensive use across industries due to its widespread applicability. Laminated plastics such as Tufnol showcase versatility of lamination, providing improved electrical insulation and mechanical performance in diverse engineering application. And so the use of lamination in composite fabrication enables the development of materials with enhanced properties tailored to specific application. Plywood and laminated plastic serve as prime examples, highlighting the effectiveness of this manufacturing technique in meeting diverse industry needs. Plywood. Plywood stands as a classic example of lamination, created through the bonding of thin layer of wood veneer with adhesive. This technique enhances plywood strength, stability, and resistance to warping, making it highly desirable for various applications. Plywood's construction method exploits the directional strength characteristics of natural wood, overcoming weaknesses associated with loading parallel to the grain. And these highlight the effectiveness of plywood as a man-made composite in various applications thanks to its enhanced properties and manufacturing process. I have mentioned laminated plastic or Tufnol. Fibrous materials like paper, woven cotton, woolen cloth, and woven glass fiber cloth are commonly used to reinforce phenolic and epoxy resin in laminated composites. Then these materials undergo a manufacturing process involving impregnation with a resin, pressing between metal plates to create solid sheets, rods, or tubes. Tufnol, with its compositions of layers of fabric or paper impregnated with synthetic resin, demonstrates exceptional resistance to heat, chemical, and wear. Its versatility and durability make it indispensable in various industries where superior electrical insulations and mechanical strengths are required. Fiber reinforcement. Reinforced concrete combines concrete compression strength with steel tensile strength, creating structures that can bear heavy loads while resisting cracks and deformations. This makes it indispensable in global construction projects. Reinforced concrete offers remarkable strength and durability, crucial in modern construction. Strategic manufacturing techniques such as reinforced placement and pre-stressing address challenges like surface cracking and corrosions, ensuring the longevity and stability of structures. Glass reinforcement plastic or GRP. GRP composites incorporating glass fibers within a polymer matrix offer a compelling combination of high strength to weight ratio and corrosion resistance, and these properties make GRP materials ideal for application demanding exceptional mechanical performance and resilience in harsh environment. GRP composites offer lightweight, durable solution with superior mechanical performance and environmental resistance, Proper manufacturing techniques, including reinforcement, orientation, or resin application, are vital for optimal properties. Their versatility and resilience make them a preferred choice across industries, highlighting their significance in modern engineering. Carbon fiber. Carbon fiber composite represent the apex of fiber reinforcement technology, offering exceptional strength, stiffness, and lightweight properties. Carbon fiber composites enable the creation of ultra lightweight structures capable of withstanding extreme conditions, driving innovation and performance to new height. Carbon fiber composites unmatched strength, stiffness, lightweight, vital in high performance industries. Fabrication processes, adhesive bonding create robust structures and driving innovation across sectors.
Hi and Assalamualaikum. I am Duratul Athiqah will be present about this subtopic 12.4 particle reinforcement. Particle reinforcement in materials. Introduction. In tough pitch copper, copper oxide particles hinder the flow of slip planes, diminishing ductility but enhancing strength compared to high purity copper. This mechanism constitutes a basic form of particle reinforcement. Next, moving on to the comparison. Similarly, stone chipping in concrete operates as a straightforward type of particle reinforcement. The implication: understanding particle reinforcement mechanism is crucial for optimizing material properties and performance. Next, 12.4.1 CERAMET, which is a short form for ceramic reinforcement metals. Introduction. Ceramic material combine the ductility and toughness of a metal matrix with the hardness and compressive strength of ceramic particles, providing particle reinforcement. For formation, certain metal oxides and carbides are bonded and sintered into a metal powder matrix, forming cement. For application, properties of ceramic composites enable the production of highly durable and abrasion-resistant cutting tools. These tools facilitate machining of hard, tough, and high-strength materials at unprecedented production rates with superior surface finishes. For manufacturing processes, metal and ceramic powders are mixed and compressed in dies to form powder complex. These compacts undergo sintering in a furnace heated to between 60 and 90% of melting temperature of the majority material present. Sintering is conducted under reducing atmosphere condition in a conveyor type furnace to prevent oxidation. 12.4.2 This subtopic is discussed about whiskers and dispersion hardening. Introduction: Whiskers are high aspect ratio crystals resembling hair with diameters ranging from 0.5 to 2 microns and lengths up to 20 millimeters. They exhibit exceptional string properties, making them valuable in material reinforcement. Next, manufacturing process. Aluminum metal is ground into fine powder within an oxygen-rich atmosphere, leading to the formation of aluminum oxide, which is alumina, on particle surfaces. Upon sintering, the resulting material comprises 6% alumina within an aluminum matrix, known as sintered aluminum powder, which is SAP. For applications, boron and carbon whiskers are employed to harden and reinforce polymeric materials. Alumina whiskers are utilized to strengthen and reinforce nickel, ensuring material strength retention at high temperatures. For conclusion, whiskers and dispersion hardening techniques offer innovative approaches to enhance material properties, catering to diverse industrial needs. Moving on to this last subtopic for 12.4, which is 12.4.3 rubber, from latex to vulcanized composite. For introduction, naturally occurring rubber is sourced from the sap of the heavier Braziliensis tree. Latex, in its natural form, presents limitations such as tackiness at elevated temperature, low tensile strength at room temperature, and susceptibility to degradation from oils and sunlight. For vulcanization process, by compounding latex with other substances and subjecting it to vulcanization, its properties transform, rendering it a useful and versatile material. Vulcanization involves mixing latex with reinforcing filler materials like carbon black and small amount of chemical such as sulfur, which accelerate the vulcanization process and enhance product longevity by improving aging characteristics. For additional information, typical products made from natural rubber are vehicle tires, inner tube, footwear, respirator masks, and gloves. Let's talk more about this rubber. Synthetic rubber, where rubber is naturally occurring. The term elastoma is often associated with synthetic rubbers, which constitute a significant sector of the polymer industry. Next, reclaimed rubber. Reclaimed rubber finds extensive use in lightly stressed application where overall strength is not critical. Next, carbon black reinforcement. The utilization of carbon black to enhance rubber properties exemplify the concept of the particle reinforced composite materials. Last but not least, conclusion. Rubber, through the vulcanization process and the addition of reinforcing fillers like carbon black, transition from a limited natural material to a versatile composite with diverse industrial application.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmas Asyraf, and now I will be present one of the subchapter from chapter 2, which is the manipulation and fabrication of polymer plastic. So, what is manipulation and fabrication of polymers? Commonly known as plastics, which is involved processes to create useful product from raw materials. This also includes fabrication techniques like molding, extrusion, and casting, as well as welding methods specific to polymers. So the first one is heat bending. Heat bending is a fabrication technique used to shape thermoplastic materials such as acrylic, polycarbonate, and PVC. It also involves heating the material to a specific temperature where it becomes pliable without melting. So the working process for the heat bending is the thermoplastic sheet is heated evenly using a heat source like a strip heater, heat gun, or oven. Then once the material reaches the appropriate temperature, it becomes soft and flexible. And then the softened sheet is then bent or formed into the desired shape using a jig, mold, or by hand. And then the material is held in the desired shape until it cools and hardens, retaining the new form. Okay, so the application for the heat bending is commonly used in industries such as signage, displays, furniture, and automotive. It also allows for the creation of curved or angle component without the need for complex mold or machinery. Then the advantages of for the heat bending is the first one is cost effective compared to molding or machining complex shapes. Also allows for rapid prototyping and customization, and also can produce smooth and uniform bends with precise control over the bending angle and radius. So for the second one is heat welding. Heat welding, also known as hot gas welding or hot air welding, which is a process used to join thermoplastic materials together. This process involves heating the surface of the material to be joining and pressing them together to create a strong and permanent bond. So working process for the heat welding is the surface of the thermoplastic materials to be welded are heated using a hot air gun or other heat source. And then as the surface reach the appropriate temperature, they become soft and malleable. And then the softened surface are pressed together firmly, allowing them to fuse and form a cohesive bond. And then the welding rod or filler material made of the same thermoplastic is used to reinforce the joint and fill any gaps. Then Common application for the heat welding is used in industries such as construction, automotive, plumbing, and fabrication. It's also ideal for joining thermoplastic sheets, pipes, tanks, and other components. Then the advantages for the heat welding is the first one is create strong, durable joint with excellent mechanical strength and chemical resistance. Also can be used to weld material of different thickness and shapes. Now the third one is solvent welding. Solvent welding is a bonding technique used to join thermoplastic material by using a chemical solvent. It works by softening the surfaces of the materials, allowing them to fuse together as the solvent evaporates. So the working process for the solvent welding is specially formulated for the specific type of thermoplastic is applied to the surfaces to be joined. Then the solvent softens partially dissolve the polymer, then creating a viscous liquid at the interface between the parts. And then when the parts are pressed together, the softened surface merge and the solvent evaporates, leaving a strong and permanent bond. So the application for the solvent welding is commonly used in industries such as plumbing, construction, and fabrication. Also ideal for joining thermoplastic pipe, sheets, fitting, and other components. And also application range from assembling PVC pipes in plumbing system. Okay, now the selection of solvent. So the first one is the choice of solvent depends on the type of thermoplastic. Then different the solvents are formulated to work with specific types of plastic such as PVC or ABS. And then the compatibility between the solvent and the thermoplastic is crucial for achieving a successful bond. Then the advantages of the solvent welding. First one is provide strong durable bonds with excellent chemical resistance, create seamless joints without the need for mechanical fasteners or adhesives, and then allow for quick and efficient assembly of components with minimal equipment and labor. The fourth one is friction welding. Friction welding is a solid state joining process used to fuse materials together without the need for melting. It generates heat through friction between the surfaces of the materials, causing them to soften and bond. So, working process for friction welding is the two materials to be welded are brought into contact under pressure. Then one of the material is rotated while the other is held stationary, then causing friction between the surfaces. Then the friction generates heat, which softens the material and allows them to bond together. Then once the desired temperature is reached, rotation ceases and pressure is maintained until the joint cools and solidifies. So the application for friction welding is used in various industries, including automotive, aerospace, and manufacturing. Also ideal for joining material with similar composition or thickness. And then application range from welding engine component and aerospace. Then the type of friction welding. First one is linear friction welding. Linear friction welding means materials are rubbed together in a linear motion to create heat. And then rotary friction welding. One material is rotated while the other is held stationary, creating friction at the interface. Then friction stir welding, which is a rotating stool with a pin is plunked into the materials, generating friction and mixing the materials together. Then the advantages of friction welding is the first one, it produce high quality defect free welds with excellent mechanical properties, require minimal material preparation and post processing, offer rapid cycle times and high production rates compared to traditional welding methods. The next one is resistant hot wire heating. Resistant heating, known as hot wire heating, is a method of heating used in various industrial and commercial applications. Involves passing an electric current through a resistant wire which generates heat due to the resistance of the wire to the flow of electricity. Working process for resistant heating is a resistive wire typically made of materials like nichrome or Contact is wound into a coil or placed in a straight configuration. Then when an electric current is passed through the wire, the resistance to the flow of electricity causes the wire to heat up. And then the wire reaches high temperature depending on the voltage and current passing through it. Then heat generated by the wire can be transferred to the surrounding materials through conduction, convection or radiation. Then common application for the resistant heating is heat sealing and welding of plastic and packaging material, heat treatment of metals for annealing, tempering, and hardening, and then heating elements in electric furnaces, ovens, and kit. Then for the environmental impact, first one is resistant heating can be energy intensive, also depending on the application and scale of operation. Then efforts to improve energy efficiency and reduce carbon emissions may involve optimizing heating processes and utilizing renewable energy sources where possible. Then advantages for the resistant heating is the first one is precise control over temperature and heating rates. And then rapid heating and cooling capabilities for efficient production processes, uniform heating across the surface of the metal being heated. Then the last one is clean and reliable operation without the need for combustion or open flames. And the next one is induction heating. Induction heating is a method of heating electrically conductive materials using electromagnetic induction. It relies on the principle of Faraday's law of electromagnetic induction to generate heat within the material. Working process for induction heat is an AC current passes through an induction coil, creating a rapidly alternating magnetic field around it. Then, when a conductive material is placed within the coil's magnetic field, the magnetic flux induces current within the material, and then the resistance of the material to this eddy current generates heat according to the Joule heating effect. And then the material heats up rapidly due to the localized and efficient conversion of electrical energy into heat within its bulk. So common application for the induction heating is hardening, tempering, and annealing of metals in manufacturing process. So heating of metal for forging, melting, and forming operations. The advantages of the induction heating is rapid and controllable heating with precise, energy efficient operation, clean and environmentally friendly, and then suitable for automation and integration into production lines for high volume manufacturing. Then the advancements of induction heating is induction heating technology include the development of high frequency induction system. Then research efforts focus on enhancing heating efficiency, expanding the range of materials that can be heated, and improving process reliability and repeatability. Now is dielectric welding. Dielectric welding, known as radio frequency welding or high frequency welding. It involves applying high frequency electromagnetic waves to generate heat within the material, causing it to soften and bond. So working principle for the dielectric welding is two or more layers of thermoplastic materials are placed between electrodes in a press, and then an alternating current, AC alternating electric field is applied to the electrodes, creating rapid changes in polarity that cause the molecules in the materials to align with this field. Then, as the molecules attempt to realign with each change in polarity, frictional heat is generated within the materials, causing them to soften and fuse together. And then the pressure is applied to the materials during heating to ensure intimate contact and uniform bonding. So, common application for the electric welding is widely used in industries such as automotive, medical, packaging, and textile. So, ideal for producing airtight and watertight seals as well as for creating complex shapes and patterns. Advantages of induction heating is produce strong and reliable bonds with excellent seal integrity, offer fast and efficient production, allow for precise controls, can be automated for continuous and repeatable welding process. Then for the material used for induction heating is the electric welding is suitable for joining a wide range of thermoplastic materials including PVC, PET, PU, TPU, and EVA, and also commonly used for welding material with thicknesses ranging from thin films to thicker sheets and fabrics. The last one is ultrasonic welding. Ultrasonic welding is a solid-state welding process used to join thermoplastic materials by utilizing high-frequency ultrasonic vibration. Creates localized heat through friction, causing the material to soften and fuse together without the need of adhesive. So, working process for the ultrasonic welding is two thermoplastic parts are placed in contact with each other under pressure, and then ultrasonic horn or sonotrode applies high frequency vibration, and then the ultrasonic vibration causes the molecules at the interface to rapidly oscillate, generating frictional heat. And then as the material softens, pressure is maintained to allow the molecules to intermingle and form a bond. Then the ultrasonic energy is focused and controlled to ensure precise and uniform melting. So common application for the ultrasonic welding is in various industries including automotive, electronic, medical devices, and packaging. Also used for sealing and welding components such as housing, assemblies, connectors, and sensors. Advantages of ultrasonic heating is produce strong and consistent welds, offer fast cycle times and high production rates, provides precise control over welding parameters including energy, pressure, and time. The materials used for ultrasonic heating is ABS, PP, PE, PVC, and PC, Also commonly used for welding materials with thickness ranging from thin films to thicker parts.
Let's explore about this subtopic 12.6 adhesive bonding. For introduction, adhesive bonding is a joining process that involves the use of adhesive to bond two or more substrates together. This technique offers advantages such as uniform stress distribution, joining of dissimilar materials, and the ability to create complex shapes. Moving on 12.6.1, this subtopic is talk about the strength of the bonded joints. The strength of the bonded joints depends on factors such as adhesive properties, surface preparation, and bonding process parameters. Proper surface treatment and adhesive selection are essential for achieving strong and durable bonds. For subtopic 12.6.2, thermoplastics adhesive. Thermoplastic adhesives Thermoplastic adhesives soften when heated and harden upon cooling, allowing for repositioning and multiple bonding cycles. They offer good chemical resistance and can bond a wide range of materials, including plastic, metals, and composite. The last subtopic in 12.6, which is 12.6.3, thermosetting adhesive. Thermosetting adhesive undergo a chemical reaction upon curing, becoming irreversible bonded and providing excellent strength and durability. They are commonly used in high temperature applications and for bonding materials with different coefficients of thermal expansion. Conclusion of adhesive bonding. Adhesive bonding is a versatile joining technique with applications across various industries, including automotive, aerospace, electronics, and construction. Understanding the properties and characteristics of different types of adhesive is crucial for achieving reliable and efficient bonded joints.
Okay, now this is my part, Muhammad Danish Daniel for 12.7 adhesive bonding of metals. Okay, for the introduction, adhesive bonding involves joining metals using adhesive instead of traditional mechanical fasteners or welding techniques. Okay, for the subtopic 12.7.1, anaerobic adhesive. The definition of anaerobic adhesive cure in the absence of air, oxygen, and in the presence of metal ions, typically found on metal surfaces. The curing mechanism anaerobic adhesive cure via polymerization when confined between metal surfaces, forming a solid and durable bond. Application commonly used for thread locking, thread sealing, and returning cylindrical components in fabrication and welding engineering. Okay, next for adhesive cured by ultraviolet light. This adhesive contains photoinitiators that activate when exposed to ultraviolet light, causing the adhesive to cure rapidly. Instant bonding, no heat required, and precision and controls. So overall, UV cured by adhesive offers a fast, effective, and precise bonding solution for welding engineering. Okay, for adhesive cured by anionic reaction, cyanoacrylates, anionic reaction. Cyanoacrylate adhesive cured through an ionic polymerization, harden when exposed to anions. The advantage, they can join materials like metals, plastic, and ceramics together, fast curing, high strength, and versatility. Okay, for activator system modified acrylysis, this adhesive cure rely on chemical activators to initiate the curing process. These activators typically contain accelerators or initiators that promote adhesive bonding. Metals, plastic, and composites for the compost. Accelerating the curing process and requires specific temperature for some modified acrylic adhesive. Okay, for adhesive cure by ambient moisture, it's a vapor. This adhesive cure when exposed to ambient moisture in the air. They typically contain reactive groups that react with water vapor to initiate the curing process. The advantages is metals, plastic, and ceramics that can combine with this kind of adhesive cure, relying on moisture from the surrounding, quick bonding, and also high level resistance. Okay, next for the epoxy adhesive is a two-part adhesive consisting of a resin, and a hardener. When mixed, these components undergo a chemical reaction to form a strong and durable bond. Advantages is versatile bonding, high strength, stable for application exposed to elevated temperatures, and flexibility curing time. It depends on what kind of compost. It could be a successful and useful person for the nation, state, and religion. Okay, next for the reduction process. It not as reduction oxidation process. Involve the exchange of electrons between the atoms or molecules, resulting in exchanges to the oxidation states. And second, corrosion prevention. They control the formation of oxides on metal surfaces. By shielding gases, we can minimize oxidation. Third, welding atmosphere. A controlled atmosphere is maintained to prevent excessive oxidation of the molten metal. Electrochemical reactions. Metal surfaces undergo electrochemical reactions due to the high temperatures involved. These reactions can result in the formation of undesirable oxides if not properly controlled. Okay, for last but not least, bonded joints. Bonded joints refer to connection between two or more components using adhesive materials. Adhesive bonding rely on fusion or mechanical fastening. Type of adhesive epoxies, acrylics, cyanoacrylics, and polyurethane. Advantages: bonded joints find application in wide range of industries, including automotive, aerospace, construction, and electronics. They are used to assemble components such as panel, brackets, housing, and structural members. Okay, for the closing, thank you for your attention. This is my phone number and my email. Can contact me for any necessary question. Thank you.